What happens when the two most reactive elements on Earth meet? That's exactly the question we're going to answer today in a series of experiments that no one has ever done before. But which two elements am I talking about? The first one is fluorine, a highly reactive and extremely toxic gas that can even burn through a brick. If pure fluorine gas were to touch your skin, here's what would happen. At this point, I want to mention something. I'm always torn between the short, punchy statements that grab the audience's attention and the much longer but more accurate explanation that kind of kills the flow. And this is one of those cases. Can fluorine cause your skin to burn on contact? Yes. If the concentration and pressure are high enough, definitely. But does that mean that your skin will automatically start burning the moment it touches any amount of fluorine? No. Reality is rarely black and white, and it's really hard to capture all the nuances every time. It was just important for me to mention that. The second element I'm talking about is cesium, the most reactive metal on Earth. It's a beautiful golden metal with a melting point of just 28 degrees Celsius. That means if you hold an ampule of cesium in your hand long enough, it will melt. But if the metal comes into contact with air, it bursts into flames. Well, again, one of those cases. You can actually have a puddle of cesium on your desk and it won't ignite. It will just quickly oxidize and get really hot. Whether or not it ignites depends on several factors like humidity, temperature and surface area. But for the sake of the video, let's just say it bursts into flames every time. Just sounds cooler that way. Here you can see what happens when I push a bit of cesium out of a syringe. What's special about these two elements is that they sit on opposite ends of the periodic table. Fluorine has the highest electronegativity of all elements and cesium the lowest. Without diving too deep into the theory, that means they are complete opposites. Or perfect counterparts, it depends on how you're looking at it. Their reaction should, in theory, release more energy per mole than any other elemental reaction. And yes, I know what you're going to say. This experiment has been done before. The YouTube channel The Royal Institution has shown the reaction of gaseous fluorine with cesium. And I really like their video. But I'm talking about reacting liquid fluorine with liquid cesium. That's a whole different story. And we won't just react fluorine with cesium, we will also test its cursed interhalogen compounds like bromine trifluoride and chlorine trifluoride. The reaction between bromine trifluoride and a piece of chocolate tells you everything you need to know about these two substances. So, you can see why no one has done these experiments before. Very few people in the world can or even want to work with fluorine. All the better that there's a professor at the Philipps University Marburg who's up for exactly this kind of fun. Professor Dr. Kraus. Probably the only person in the world who not only has the knowledge and equipment, but is also willing to carry out something this insane. Just the opportunity to visit Professor Kraus' fluorine lab and join the experiments was enough to bring NileRed all the way to Germany. Together with Nigel, Professor Kraus and his PhD students, we first set out to find a suitable location for the experiments. Once we had found it, it was time to prepare everything. As some of you may know, fluorine is a gas, but today we will liquefy fluorine at -196 degrees Celsius and then add cesium to the liquid fluorine. Because fluorine reacts with almost all materials, we had to make special containers out of PFA to hold and liquefy the fluorine. If you want to learn more about the techniques used in a fluorine lab to safely handle this reactive gas, check out my previous video on fluorine. Once these vessels are prepared, they are connected to what's called a fluorine line. As you can see, the fluorine cylinder containing 100% fluorine gas is kept in a separate metal box inside a fume hood and can be operated from the outside. By pulling a vacuum on the container and checking if air leaks in, we can test if the vessel is completely sealed. As it turned out, there was a small leak in one of the fittings.
He sees the pressure in the line,
still leaving, yeah.
and he closes it, and then he sees that the pressure is rising. He basically knows that there's a leak.
Yeah.
Oh, it leaked.
Yeah.
I mean, these are like we're saying the small details of what you have to do.
Yeah.
Because otherwise you just do the YOLO method, and you're like, yeah, I'm used to tightening this stuff. I think it's pretty good. You fill it with stuff, and it just like.
Once that was fixed, we could open the valve to the fluorine cylinder. We then poured liquid nitrogen into a Dewar flask surrounding the PFA tube, cooling it down so much that fluorine gas begins to condense.
So you can see the fluorine already here inside. Well, this is our high precision measuring system. So we know how much fluorine fits in like 1 centimeter of this PFA, and so you just measure it, and then you know the amount of fluorine.
How much is it per centimeter?
So it's like 2 milliliters.
Okay.
In this size.
Yeah.
So I removed the rest of the fluorine from the line, so now we can open the line without.
How do you remove the fluorine?
Just vacuum, argon, vacuum, argon.
But
So
fluorine has no chance of reacting with argon, right?
No. Sadly not.
Why is that?
But I wanted to argon. I wanted to argon fluoride just. Okay, and now
So that's just argon flowing.
fluorine.
Wow.
And now you're one of the few people on Earth who have seen liquid fluorine. Inside that vessel, under the right conditions, it looks almost harmless. But just a single drop of this liquid would be enough to kill you. To run multiple experiments, we prepared several vessels with liquid fluorine. These must be continuously cooled because fluorine cannot be liquefied under pressure. If any of these tubes warmed up, the pressure would cause them to burst, spreading toxic fluorine gas throughout the room. Definitely something you want to avoid. As previously mentioned, we are also going to react cesium with chlorine trifluoride. This also requires filling PFA tubes with the highly dangerous gas, again by condensing it using liquid nitrogen. It has a relatively high boiling point of approximately 12 degrees Celsius and can be liquefied under pressure. Nevertheless, we are also cooling these tubes to keep the chlorine trifluoride a solid until we use it.
The yellow color of the chlorine trifluoride. Normally, chlorine trifluoride is a colorless liquid. Yellow color comes from chlorine impurities, which are present because the chlorine trifluoride was used already, and we use this recycled for the experiment we will do, because fresh chlorine trifluoride is very expensive, hard to make, so we use this pre-the experiment, but it's reactive enough. Because the main part of the chlorine trifluoride is
Yeah, I can do the operation. Yeah, you can see here the frozen chlorine trifluoride.
And finally, we will react cesium with bromine trifluoride. Since this is already a liquid at room temperature, we don't need to cool it. It can simply, in quotation marks, be filled into the tubes.
So you will open it right here?
Yeah, so maybe you can a little bit of space. Yeah, sometimes there are some clouds of HF or something else coming out when opening it.
Now that all the highly toxic substances are ready, it's time to prepare the air-sensitive metal, cesium. This research group doesn't just have several kilograms of it stored in steel containers.
I have...
That's their cesium.
Oh.
Yeah. And these were all filled with rubidium here.
They also have a 1 liter bottle filled with cesium inside a glove box. A glove box is a sealed chamber filled with argon or another inert gas where air-sensitive substances can be safely handled. Everyone who's ever worked inside a glove box knows how clumsy it can get with those thick gloves. And it certainly doesn't get easier when 5 people with 2 cameras are watching your every move. My respect to Juliana for keeping her cool despite all of that. Since cesium melts at 28 degrees Celsius, she wrapped a heating band around the bottle to liquefy the metal. Once it was liquid, it was poured by hand into a beaker. Not a sentence you hear every day. Do you remember what happened when I pushed a few drops of cesium out of a syringe outside the glove box? Being able to handle the metal so casually almost looks unreal. But cesium is so reactive that it would still slowly oxidize over time, even in the glove box. From the beaker it was drawn up into syringes. To prevent the syringe tips from igniting when removed from the glove box, the opening was sealed with PFA caps. Anything going in or out of the glove box has to pass through an airlock, which is purged several times with argon to prevent any air from entering. Now, the big question: how do you get the cesium from the syringes into the highly toxic fluorine, chlorine trifluoride or bromine trifluoride? You certainly won't find a volunteer willing to do it by hand. So I designed a mechanism that rapidly pushes the cesium out of a syringe from a safe distance. But of course, this device can't be 3D printed, since any plastic would burn immediately on contact with fluorine. And that's where today's sponsor, PCBWay, can help. On PCBWay's website, you can simply upload your 3D model, choose a suitable material, and they handle the rest. I had the entire mechanism custom made from stainless steel. They even added threads wherever needed. No problem. So, a huge thank you to PCBWay for sponsoring this video. If you need custom parts printed or machined, check them out. The link is in the video description. I tested the mechanism thoroughly beforehand and everything worked as intended. But during the demo in the lab, this happened.
Ready? 3, 2, 1. No.
Definitely not what you want during the real experiment. But with a bit of Teflon grease, the mechanism worked like a charm. Now it was finally time to take everything outside and get things ready. We secured the test area and arranged all necessary equipment, like a calcium chloride solution to neutralize hydrofluoric acid. Once everything was in position, I gave the PhD students a final walkthrough on how the mechanism works.
Also mit dem Sicherungsstück auf keinen Fall. Wenn der hier drin ist, kann die nicht losgehen.
It's impossible. Nothing could possibly go wrong.
Okay, also er ist selber hier.
Ja, absolut, ja, okay, ja, also, okay, dann vertraue ich dem Ganzen jetzt. Mehr, jetzt will ich rein.
Running 2 screws.
I just made 2 holes because maybe.
You gotta be symmetrical.
Yeah, that's one thing.
But now that there's a hole there, I feel like it needs a screw. People online will say you forgot one.
And we did a practice run with water in the syringe to rehearse and check the position of the high-speed camera.
Oh, I see they've pastified it with some goo.
Pastified.
It seems to be good now?
Yeah, we've tested it a few times with water.
I see it pastified.
Oh, it's really looped up. I mean, and it feels so much different. And we tested it with water on the high-speed cameras.
And it looks nice?
Yeah, it looks nice.
Nice.
It's not a phantom, but it looks nice. Yeah.
So cesium is not radioactive. So these are, the stickers are for a different purpose. So.
When we tried to mount the first syringe, we noticed it was too full to fit into the mechanism. Or at least we thought it was too full. In reality, the syringe just wasn't seated properly in the stainless holder. But since we didn't know that yet, we decided to squeeze out a bit of cesium to make the syringe fit.
Ja, das sollte reichen.
And this is where you can clearly see why cesium is the most reactive metal in the world. As soon as it hits the air, it ignites. When Professor Kraus tried to mount the syringe in the mechanism, this happened.
I think if the plunger hits the back. Oh my god. It's the back.
Oh my god.
machen wir da damit? Da, hier ist reichlich Cesium drin, da müssen wir uns später was überlegen.
And when we tried to prepare the second syringe, it caught fire again. It became clear that opening the tip to release some cesium wasn't an option.
Yeah.
Oh no, what happened?
Passt das?
Jetzt.
Das riecht auch gut.
Yeah, that's what happens when cesium gets on your glove.
Let's quickly talk about what I think is happening here, because in my opinion it's quite interesting. Sure, cesium is very reactive, and as you have just seen, it can ignite in contact with air. But this reaction looked different. And most importantly, the reaction took place after the syringe was already sealed again with the cap. So my theory is that the cesium reacted with the cap itself. They are made out of PFA, a fluorinated polymer, and the affinity of cesium towards fluorine is quite high. At room temperature, cesium doesn't seem to be able to rip those fluorine atoms from the PFA. Although, you could already see that when we put these caps on the syringes inside the glove box, they got black where they touched the cesium. When we then pushed the metal out of the syringe, it probably got hot enough that when we replaced the cap, it was able to react with the polymer. At least that's my theory. If you have another one, let me know in the comments. Luckily, we quickly realized that the problem wasn't the volume of cesium, but the improper mounting. Once fixed, we could finally do a real test run with cesium.
Wollen wir da eigentlich Wasser reinmachen? Einfach, ich meine, dann wird Cesium abreagieren. Quenchen nennt man das ja, glaube ich.
Wollen wir Wasser reinmachen? Mach Wasser rein. Wollen wir Wasser rein?
Schön. Mach ich mein Handy schon mal da.
And now it's time for the real experiments. We started with bromine trifluoride. Professor Kraus and his student opened the nitrogen-cooled tube and placed it under the syringe.
Drei, zwei, eins.
As you can see, these substances are so insanely reactive. The cesium already reacts with the gaseous bromine trifluoride and barely touches the liquid. In the end, very little of the bromine trifluoride was consumed.
It's still sparking. Yeah, there's a lot of BRFP left. It's all reacting in the gas phase.
Da ist noch so viel Trifluorid drin.
But there was another problem.
So it seems that the cesium had solidified. And it was not pushed in.
Now we had to disarm the setup. To do that, Professor Kraus froze the bromine trifluoride with liquid nitrogen and then carefully removed it. Since the first test didn't go quite as expected, we tried a second bromine trifluoride run.
How much cesium is that?
It's 5 point something milliliter.
5.
What amazed me again is how the cesium reacts entirely in the gas phase, leaving most of the bromine trifluoride untouched. The high-speed footage also shows a pulsing reaction. I don't know exactly why. If you have any idea, let me know in the comments.
Smells great.
Cesium fluoride, salty. So you see the reaction seems to be to start in the gas phase, and then we have some reaction with the bromine trifluoride. But not everything is reacting because we are in so much excess of bromine trifluoride. We need less bromine trifluoride.
I mean, I could fit a 10mm syringe away. So even more cesium. so it just sinks to the bottom no matter what.
Yeah, because you see it just penetrates maybe the surface,
And then just gets
the surface,
blasted.
and then it's blasted automatically.
All unused bromine trifluoride that did not fully react was stored safely and quenched later. After bromine trifluoride, it was time for the even more reactive chlorine trifluoride.
It's now CLF3 we're doing next. Sorry? CLF3 we are doing next.
So we are pre-cooling the chlorine trifluoride, that it won't blow up in our face when we open the vial.
Just to decrease the vapor pressure of the chlorine trifluoride.
Wow!
Why the first run caused a delayed explosion is still unclear. Again, let me know if you've got a theory. We immediately did a second test. This time, no delay, and the reaction was so violent it ripped the PFA tube out of the clamp.
It's still burning in the inside. See the fire, come over here. See? Still burning. What you smell is chlorine trifluoride.
Smells good.
Well, it smells very similar to fluorine.
Yeah.
Wie viele Leute haben in ihrem Leben schon Chlortrifluorid gerochen?
Wie viele Leute haben in ihrem Leben überhaupt das schon mal gesehen in echt?
After each experiment, all surfaces were sprayed with calcium chloride solution to convert remaining fluorine compounds into less dangerous calcium fluoride. And now, finally, it's time to react liquid fluorine with cesium.
So, 3, 2, 1.
The slow motion footage clearly shows that even the vapor above the liquid fluorine causes such a violent reaction that the tube gets launched away and most of the cesium never even reaches the liquid. Luckily, we had more syringes and repeated the experiment.
Oh.
Dein Kopf weg.
The PFA tube got blown away again, and we spent half an hour looking for it. At the end, we had one more tube of liquid fluorine left, but no more syringes of cesium. That's when Professor Kraus had a brilliant idea.
That seems pretty plausible, yeah. It means it reacts like instantly.
In the air as soon as it hits the gas.
Ready for what?
Petroleum ether.
Petroleum ether and fluorine.
At this point, I want to give a huge thank you to several people. To Elias from Elias Experiments, who planned and filmed this video with me, to Felix, who organized the high-speed cameras and worked through the blistering heat to get these incredible shots, to Professor Kraus, PhD students who gave up an entire day for these experiments,
Das ist nichts für YouTube, okay? Nichts für YouTube.
and of course to Professor Kraus himself, who made all of this possible. Thanks to him, we were able to capture reactions that had never been seen before. I've already talked with him, and if you have ideas for more experiments with fluorine or chlorine trifluoride, drop your suggestions in the comments. Maybe we can make them happen. And finally, thank you to Nigel and Reggie, who traveled all the way from Canada to visit Professor Kraus' fluorine lab and witness these experiments firsthand. It was an amazing time. If you like my videos, consider subscribing or joining me on Patreon. You can find a link in the video description. I really hope you enjoyed today's video. Other than that, thank you a lot for watching.
So,
The sign of a job well done.
this is the sweat of hard work done.
Do you find it nerve-wracking when you have to go close and do all those experiments? You've done them for so long with that? Yeah. Yeah. I mean, the general rule I find...
I've done much dangerous things.
But I think the general rule is like, if you've put the proper safety protocols in place, you should obviously be careful, but you shouldn't be like afraid.
Yeah, exactly.
If you're afraid, then...
No, there's no need to be afraid.
Yeah, if you're afraid, then you probably shouldn't be doing it.
There is no need to be afraid.